Next, let's see exercise 8. In this one, we have to complete the proof of the matrix version of theorem 662. We have already seen and proved the operator version. For this, however, we don't actually have to do anything. Since we have the operator version available to us, we can use the association between operators and matrices. That is the result that we know that operator algebra and matrix algebra are isomorphic. We can just use that and have the matrix version as a consequence. So that means we are going to use the original theorem 662 in its operator version and theorem 632. Okay, so by these two results we have the following. By theorem 662 and theorem 632, we have this. Let A be any n by n matrix and K be the splitting field of the minimal polynomial of A over F. Then there exists an invertible matrix C in Fn such that CA, C inverse, is in Jordan form. And that is the matrix version of theorem 662. So that's what it is. Next, let's see 9. I have already, I should say, drawn the matrix because it takes some time to write these things here. So let's now complete the question, the statement of the exercise. An n by n matrix is given, which is of course that one, where almost all the entries are 0 except the sub-diagonal entries. You know that this is the leading diagonal. The diagonal above that is super diagonal, but there is also one diagonal below that, that is the sub-diagonal. The sub-diagonal entries are all 1. Prove that this n by n matrix having ones on the sub-diagonal and zeros elsewhere is similar to the matrix Mn. You remember Mn also is like this, but there the super diagonal entries are all 1 and the other entries are 0. This is actually not very difficult. You just have to know the matrix that will give this similarity. In fact, for our writing convenience, let's give this matrix a name. Let us call this, say, A. Okay, since it's the, in the question it's not given any name, so when you start the solution you can write let A be the given matrix. That I am not writing, okay, it's understood that this is A. Consider the matrix B, which is also an n by n matrix, so it belongs to the matrix algebra Fn, where now we write what B is. B also has almost all its entries 0 except the other diagonal, the diagonal that a square matrix has other than the leading diagonal. This is one diagonal, that other diagonal, and there all the entries are 1. So it will look like this: 0, 0, 0, 1, 1, 0, 0, 1. Then after that, of course, we have only zeros. And then finally 1, 0, and the other entries are 0 in the last row. So this is my matrix B. It turns out that this matrix is invertible. And its inverse is B itself. And this verification I am leaving to you. Then one can verify that B is invertible with B inverse equal to B itself. What do you have to do to verify this? You just show that the square of B is the n by n identity matrix. That's it. Which in fact is an easy thing to do. Also, so once you know that B inverse is B, calculating B inverse won't really be a big problem. I mean, you know the inverse, then it's just a matter of multiplication. Also, it turns out that B inverse, which is simply just going to be BAB, is in fact Mn. That is why the given matrix A is similar to Mn. Next, number 10. If our underlined field F has characteristic P which is positive, so you know that P is a prime. Prove that this matrix, this 2 by 2 matrix A, whose first row is 1 alpha and the second row is 0 1, satisfies this equation. The pth power of A is 1, and 1 in this context of course is the 2 by 2 identity matrix. So let's see how this can be solved. It's just a matter of calculation, and because we have a 2 by 2 matrix, it's quite easy. You just have to figure out the pattern of the powers of A. A looks like this. How does A squared look? How does A cube look? We have A squared 1 alpha 0 1 1 alpha 0 1. Actually, if you remember, we have already come across matrices of this type in one of the exercises in group theory. You may remember this because the product that you are going to see here will in fact not change these entries. First row, first column, second row, first column, second row, second column entries won't be changed. Only this one will be changed, and that too, these two will be added. The effect of multiplying these matrices on this entry is addition, sum. Let's see. Let's do the multiplication. First row, first column, 1 times 1 plus alpha times 0 is 1. 1 times alpha is alpha plus alpha times 1 is alpha. That means alpha plus alpha is 2 alpha. Or if you use both of your hands, you can synchronize the row and columns like this. First row, first column, 1 times 1 plus alpha times 0. 1 times alpha plus alpha times 1, 2 alpha. Second row, first column, 0 times 1 plus 1 times 0 is 0. Second row, second column, 0 times alpha plus 1 times 1 is 1. So you see that these entries haven't changed, but this one has changed, and it's just the sum of these two entries, which are the same in this case, so 2 alpha. So this exponent 2 appears here. And let's see how A cube looks. A cube can be written as A squared times A. So we already know how A squared looks. And then A is 1 alpha 0 1. You can maybe guess that here also we have to add the first row, second column entries, and that's true. One plus 0, 1. Alpha plus 2 alpha, 3 alpha. 0 plus 0, 0. 0 plus 1, 1. So here also the exponent 3 appears as the coefficient of alpha. Continuing like this, we get A to the power t. So if this pattern persists, which it will, okay, it will persist. If you calculate the fourth power, you will see, because now you have, you not only see what the pattern is, but you also know how the pattern has come. So obviously 3 alpha and alpha are going to be added in the next one, so that will give you 4 alpha. In general, if in general means the pth power is going to look like this: 1 p alpha 0 1. However, our element alpha is coming from the field F, which has characteristic P. So P alpha in that field is 0. So that way we get 1 0 0 1, which is nothing but the 2 by 2 identity matrix over F, which also we denote by 1. So that's how we get A to the power P equal to 1. The next one is also similar, but this time F has characteristic 0, the other case where F doesn't have finite characteristic. If F has characteristic 0, prove that the matrix this time also has the same form. It is still 1 alpha 0 1, satisfies A to the power m equal to the identity matrix 1 only if alpha is equal to 0. Only if has a specific meaning. Okay. So what type of implication are we being asked to prove here? What should we mean by only if? If in place of only if we had if, simple if, then the implication would have been like this. If alpha is 0, then this is true. That would be the implication if we had if here, but we have only if. It's the other implication. That is, if this is true, then we have to prove that alpha is equal to 0. This is what we have to prove here. Okay. We can save our labor somewhat by noting that in the previous solution also, the powers of A that we calculated had that specific form. Now that really does, the form in which the powers come, the matrix powers come and their entries come, that form is not dependent on the fact that there F was of characteristic P, whereas here F is of characteristic 0. The form, the entries, how the entries look, that has nothing to do with what the characteristic is. Here also, if you calculate the powers of A again, A square would still be 1 2 alpha 0 1, A cube would still be 1 3 alpha 0 1. So we can, without again doing those things, straight away write this. From the previous solution, we see that one m alpha 0 1. Okay. In spite of the fact that there the field is of a different nature. So, if this is equal to, let me write one first, which here has this meaning, then m alpha has to be equal to 0. Oh, okay, hold on. I forgot to write one crucial thing. Otherwise we cannot say anything. For a positive integer, sorry about that. Only if this. Okay, so we are now having this. Since f is of characteristic 0 and m is a positive integer, so m alpha is 0 means alpha has to be 0. We must have alpha equal to 0. That is why alpha is 0. Okay, so this solution ends here. We will see the other, the subsequent exercises in the next linear algebra video. So let me end the video here itself. And tomorrow, as usual, we have analysis, where I forgot what we are doing right now. The section that we are in right now in analysis, one exercise is still there for us to do. So tomorrow we will solve that. So see you tomorrow with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.